Welcome to Data Science with EJD. In this video, I'll be talking about classification metrics. Don't forget, I've been talking about classifications, knowing that under supervised learning, which we are broadly considering, we have two major tasks of classification or regression. And that is having seen that under machine learning, we have supervised, unsupervised, and reinforcement learning. So, and since you've been I mean, of course, supervised learning and unsupervised learning are the things you have under machine learning. So for classification metrics, you are looking at those metrics, those ways to measure your model. You already know the procedure for modeling is you get your data, you clean it up, then you split it into train sets and test sets. Then you train your model, and then with that, now you predict with the model you have trained, and then you now need these metrics to measure the performance of your model to see how well they are doing. And for classification metrics, we have some specific kinds of metric. For classification tasks, rather, we have some particular metrics, and we are focusing on this in this video. We've been using them a lot, but here we dig a bit deeper into them. All right. So the learning objective here is to use things like confusion matrix. Let me put the line numbers, right? So use confusion matrix, precision, recall, F1 score, and ROC to evaluate a classifier using multiple metrics. So you use a classifier, maybe one of the ones we've used before, and then use all these metrics across to see how all of these perform. How all of this do. So in the introduction, why use classification metrics? That's a very good question, right? Classification models assign data points to classes. So after training, we must evaluate how well a model performs on unseen data. Relying on accuracy alone can be misleading. So if you take accuracy, sometimes maybe the accuracy is 90%, but maybe other metrics can say otherwise. So you need to look at various metrics to be very sure that you need to be convinced. You don't just work with accuracy and just walk away, right? You want to be sure. So relying on accuracy alone can be misleading, especially when classes are imbalanced. Cost of errors differs across classes. Therefore, we use a suite of metrics to get a multi-dimensional view of performance. So, for you to be able to recommend a model, you want to be sure you have checked different metrics and see that they perform very well across these very different metrics. Metrics. So, first of all, we talk about the confusion matrix, which is the foundation of all these classification metrics, right? By definition, a confusion matrix is a 2 by 2 table for binary classification showing predicted versus actual class labels. So you see on the here you see actual positive, actual negative. Since you're predicting, right? Since you're classifying, right? So something may be positive and the algorithm says it is negative. That is a false. That is a false. Uh, that's a false negative, right? Then something may be positive and the algorithm says it is positive. That's true positive. Something may be positive and the algorithm says something I mean, all those dynamics. So you have actual positive, actual negative, then predicted positive. So if something is actual positive and the prediction is positive, that's true positive. If something is positive and the prediction is negative, that's false negative. If something is negative and the prediction is positive, that's false positive. If something is negative and the prediction is negative, that's true negative. So that's that's the basic thing about a confusion matrix, right? So at the end of the day, you are very interested in true positives and true negatives. So whatever you get across the diagonal, those are the things you actually are interested in. So most of the times, for you to know that a classifier has done a good job, you want to be sure, you want to see false positive and false negative zero. I think from what we've done in the past with Iris dataset, that happened a lot. So we're able to get true positives and true negatives, and then zero zero for false negative and false positive. So anything false, we are not interested. We're only interested in the true ones, right? So we can actually extend this to multi-class stuff. So for multi-class classification, the confusion matrix becomes an n by n matrix, where n is the number of classes, and each row represents the actual class, and each column represents the predicted class, right? So things become a bit trickier when you're dealing with multi-classes, like you have multiple stuff like that. Okay, so that's what we have there. For a multi-class classification, the confusion matrix becomes an n by n instead of just 2 by 2 that we have. It becomes n by n, where n is the number of classes, Each row represent the actual class and each column represent the predicted class. So just like we have like something close to that. So the evaluation metrics derived. So the confusion matrix is the basic of is the basic metric we use. And from there, we can now have other evaluation metrics derived from the confusion matrix. So first of all, we have accuracy, which we've been talking about a lot. So we already know the idea of true positive, true negative, and all that. So the accuracy is actually measured by true positive plus true negative all over true positive plus true negative plus false positive plus negative, all the possibilities, right? So we want the true one. So if, for instance, the true positive plus true negative is equal to is equal to all of this. If, for instance, the false positive and false negative are zero, that's where you get an accuracy of one, just like we've been getting with the iris data set, right? So the pro is it is very simple and intuitive. I mean, just like what I've just explained now. So if you get an accuracy of 100, or that's 1.00, that means that the false positive and false negatives are zero each, right? Then the con is like it can be misleading on imbalanced data. So if you have imbalanced data, this may not be the best thing to use. Then after accuracy, we have precision. So precision, now we have true positive all over true positive plus false positive. So it's the battle of positives, right? So what it answers is that of the instances predicted as positive, how many are actually positive? That's the idea of precision. So the use case is when false positive are costly, e.g., spam filter marking important email as spam. So you have an important email and it is classified as spam. That is not too good. In fact, that's not good at all, right? So you want a high precision as much as possible. To get a precision of one, it means that false positive is also zero. In that case, you just have true positive over true positive. That's the number of true positive is equal to total true positives or total positives available. So in that case, you have a precision of 1.00 100%. Then talking about recall is true positive all over true positive plus false negative. That's what recall is. So that's sensitivity or TPR. So what this answers of all actual positives, how many did the model correctly identify, right? So false negatives are actually positive that have been identified as negative. So that is why recall is useful. So the use case is when false negatives are costly. So you don't want any false negatives. Like when somebody has cancer and the diagnosis is saying otherwise. All right. So that's a false negative and that's really costly. We don't want that at all. So you see, each of these things have their use cases. Then we have F1 score, which is the harmonic mean of precision and recall. So of course, the precision and recall have pretty simple formulas. So once you compute those, so if you want to, if you want get the harmonic mean of this, so you get 2 times precision times recall over precision plus recall. So this balances both types of errors. So if you have costly false positive and costly false negative. So you can use F1 score to balance out these things. So the F1 score may be a very nice way to go if you need a balance of these two. So this is preferred when data is imbalanced or when both types of errors are important. Just like I said, so but it balances both types of errors like we see already. And then we have specificity, which is true negative rates. So this is opposite of recall. Now this is focused on the negative class. So of all the true negatives, are we sure the true negatives are really good? Like they are how accurate is that? So you get a specificity of one if all the false positives are zero, right? So it means you have true negative over true negative, same. So then you have the ROC curve and AUC. So the ROC is the receiver operating characteristic curve, right? So this plots true positive rate, that's TPR, which is the recall, versus false positive rate, FPR, at various thresholds. And then false positive rate is actually FP over FP plus TN, like we've seen already. And then we have the AUC, which is area under the curve, and the score is usually between 0.5 and 1.0. This measures model's ability to separate classes. So when AUC is 1, that's perfect. You have a perfect classifier. But when AUC is 0.5, you have no better than random. So it's just neither here nor there in that situation. So let's look at an implementation in Python scikit-learn. So by now we are used to most of the algorithm. In this case, we are using the breast cancer data set, right? So from the data set, we load the breast cancer data set. Then, of course, we have the model selection, talking about the train test split. And here we are using, though we are working with classification metrics, right? So we are using logistic regression here. So I will now use all the metrics to measure the performance, right? So accuracy score, confusion matrix, precision score, recall score, F1 score, ROC curve, ROC-AUC score, confusion matrix display, classification reports, and blah, blah. So I want to visualize all this using matplotlib as usual. So we load the data set now, XY, load breast cancer, return XY true. Then we have X-ray next test. That's this whole splitting thing. And then we have something additional. You stratify it according to Y, right? So we train the model using logistic regression with 10,000 maximum iterations. We can increase that or reduce that depending on whatever we want. Then we have the model fit. These are actually where the model training takes place. And then we are doing prediction here, and then we have a probability here. So just like we saw the other time, logistic regression, gives the probability that you are going to have a true or false kind of scenario, and then you can evaluate after that, right? So then we can have the to evaluate, right? You do confusion matrix, classification reports, and all the other ones, accuracy score, precision, which you have already understood how all of these things happen. Then we have the ROC curve and AUC also. So FPR, TPR, ROC curve, Y test, Y prop. So you're plotting all of these things. So we run this, and then it takes a bit of time, and then that jumps out. Yeah. So we have the first confusion matrix. So here you see that we have this should be like true positives, right? Yeah, I think that's true positives up there, and it's particularly nice that we have that a high value of that. Yeah, true positive, true negative. Yes, so true positive, true negative, and then down here we have true positive, true negative, and then we have false positive, false negative. Yeah. Okay, so it's particularly good that the true positives are 48 and the false negatives, true positive, true negative. So that's really cool. And then here we have false positive and false negative. There are few. So that shows a nice performance of the model. The overall accuracy is 0.96 roughly. And then we have everything is 0.9 something. That's really nice. Right. So that goes. So you can now, so with this, with all the explanations we've done, we can now better understand some of these values now based on all those calculations up there. Then we have the ROC curve right here. It shows some near perfection kind of thing. So the AUC is roughly 1.00, right? So interpreting the result, right? Suppose the output is, we are not even supposing that's what the output is, right? I've really corrected all this, right? So accuracy is 0.96, right? Precision is 0.95, recall is 0.99, F1 score is 0.97, and AUC, as you see from here, is 1.00. That's 100%. So even for the breast cancer data set, this is looking very well. So the interpretation, high accuracy, but we validate it using precision and recall to ensure robustness. So we have precision and recall also to be sure we have robustness. The F1 score is not doing badly too. So it balances out between precision and recall, right? So we also have high recall, which ensures that most actual positives are correctly identified, especially important in domains like healthcare. So we want the correct thing in diagnosis, especially for something like cancer. So high AUC implies that the model has strong separability between positive and negative classes. It performs well across all classification thresholds. So that's a good model right there. And maybe the data set is also pretty easy to follow. So when do you use each metric, right? So when there's class imbalance, you want to use F1 score and AUC to be sure there's to balance between recall and precision. Then when the cost of false positives is high, so uh when if you call something positive and it is actually not positive, then precision is really important. Like in the case of spam filtering, right? You want if you call a message spam when it is not spam, that's a problem, right? Then cost of false negatives is high. like in the case of breast cancer, right? You say something is negative, but it is actually positive. That's a problem, right? In fact, I know of an instance where someone actually had that problem. The person was diagnosed as not having cancer, whereas the person had cancer, and that ultimately led to the person's you know a problem. Okay, so balanced importance of FP and FN. If you want to that balance between false positive and false negative, F1 score is the right thing for you. Then, if you need probabilistic threshold tuning, then you need ROC and AUC. In summary, you have the metric sheet cheat sheet. All right. I mean, you have the formulas again, the accuracy, quick performance that can help with quick performance check. So at least first, if you check accuracy, you can have a level of confidence that, oh, in fact, if you already see accuracy to be something very low, I mean, it means you may have to do something extra. But if you see the accuracy very high, then you can now go ahead and check other things like precision. When FP is costly for spam detection, for instance, recall when false negative is costly, like for disease detection, then F1 score, which is harmonic mean of P and R, which is balanced measure on imbalanced data. The ROC curve, that's true positive rate and false positive rate. Visualizing threshold performance trade-off, right? AUC, that's area under ROC, and that's overall discriminatory power. So the optional extensions for this can be things like precision recall curve better than ROC for imbalanced data. You can do cross-validation with metrics, which evaluate stability across folds. Then you can do multi-class metrics, use things like average is macro, micro, weighted in scikit-learn. So with this, we come to the end of this very interesting video talking about classification metrics. So, and of course, with this, we have also come to the end of course, I could go on and on with other classification algorithms, but with the ones we have done are good enough, right? And then we are ending with this metrics thing. So I will come to the end of this. Thanks for listening. Let me know how helpful this video is for you. If you have not subscribed, you want to do that right now, and don't forget to hit the notification bell so you can always get alerted each time a new video is released. Membership is open on my channel. You can get extra benefits by signing up as a member. Of course, if you don't become a member, not a problem. As a subscriber, you still have you still have your regular privileges for sure. All right, and don't forget by checking the description box either on Facebook or on YouTube, you can get access to my code sheets and my data sets if any, and then try hands on as I do this thing, so you do it alongside, so you can really the ideas can really register with you like that. Also, don't forget to like and share so that more people can have access to this great content that I have going on here. Till I come your way again, keep doing data right. Bye.